Hey guys, in this lesson we would understand how to calculate equilibrium concentration when we are given K equilibrium or equilibrium constant. Let's go over the first question. At 1100 Kelvin, hydrogen and iodine combine to form hydrogen iodide gas as shown. So this is the reaction. H2 plus I2 gives you 2HI. Everything is gaseous. At equilibrium in a 1 liter reaction vessel, the mixture of gases contained 0.30 moles of hydrogen. So we are given 0.30 moles of hydrogen, 1.3 moles of iodine, and 3.4 moles of hydrogen iodide. And it is important to note here that these moles are given at equilibrium. We are supposed to determine the value of K equilibrium. We know K equilibrium is nothing but ratio of products to reactants. And this is how we write down concentration of the product raised to the power of 2 over concentration of hydrogen, that's the reactant, because the stoichiometric coefficient is 1, so we put the power as 1. Next is concentration of iodine raised to the power of 1 as well. So this is the product of the reactants. And on the product side, we just have one compound, so we write down HI square over H2 times I2. So this is our K equilibrium equation. Now we are supposed to find out K equilibrium, but first let's see, are we given the concentrations of HI, H2 and I2? And we notice here that we are given the moles of each of these: hydrogen, iodine, and hydrogen iodide gas, and all these moles are given at equilibrium. We can use these moles along with the volume to get the concentration of hydrogen iodide, hydrogen and iodine. So let's first get the concentration of hydrogen iodide. We know concentration is number of moles over volume. So the number of moles of hydrogen iodide is 3.4. We put 3.4 divided by volume is 1 liter. So it's over 1, which is nothing but 3.4 itself. Similarly, concentration of hydrogen is 0.30. So we have 0.30 divided by 1, which is 0.30 itself. Next we have is concentration of iodine, that is equal to 1.3 divided by 1, which is equal to 1.3 moles per liter concentration. Now we use all of these concentrations in this equation, and all we have to do is just solve the equation. Therefore we get K equilibrium is equal to HI concentration is 3.4, but we notice that 3.4 is raised to the power 2, so we're going to square it, over hydrogen concentration is 0.30. So 0.30 to the power of 1 multiplied by 1.3 to the power of 1 as well. We just have to put this all on the calculator, and that will give us the K equilibrium or equilibrium constant value, and we get 11.56 divided by 0.30 times 1.3, which is equal to 11.56 over 0.39, that is 29.6. So the K equilibrium value is 29.6 in this case. So all we have to do in this question is just plug in all the values of the concentrations at equilibrium. We get that by dividing the moles at equilibrium with the volume, and we solve this equation for K equilibrium. The next question is, a chemist is studying the following reaction at a certain temperature. It's SO2 gaseous plus NO2 gaseous gives us NO gaseous and SO3 gaseous. In a 1 liter container, the chemist adds 0.17 moles of sulfur dioxide to 0.11 moles of nitrogen dioxide. At equilibrium, the concentration of sulfur trioxide is given to us as 0.089 moles per liter. They want us to find out the value of K equilibrium. So let's write down what is K equilibrium going to be first. We know K equilibrium is going to be equal to the product of the products. It's NO concentration multiplied by SO3 concentration raised to the power of 1, because the stoichiometric coefficients are 1, no value means it's 1, divided by SO2 concentration raised to the power of 1 multiplied by NO2 concentration raised to the power of 1. Now we have to remember that these concentrations should be at equilibrium. We notice here is that at equilibrium we are just given the concentration of sulfur trioxide. So we are just given this. We are not given the concentration of anything else. So that is our first goal to figure out. Once we get the concentration at equilibrium for NO, SO2 and NO2, then we will be able to solve for K equilibrium. So from here, first we have to find these three concentrations. And for that, they have given us a help. And that help is that when we start this reaction, volume of the container is given to us, and the initial moles of sulfur dioxide and nitrogen dioxide is given. So we are given the initial moles of both the reactants. That means we can find out the initial concentration of SO2 and NO2. So SO2 initial concentration is going to be the moles of SO2 that we start with divided by the volume of container, and that is going to be 0.7, and that is going to be 0.17 divided by 1, which is 0.17 by itself. Next, we can get the initial concentration of NO2 with the same method. It's the initial moles that are present, which is 0.11 divided by 1. That gives us 0.11 moles per liter. Concentration units are always moles per liter because we're dividing moles with volume in liters. Now we need to notice here that these values we cannot substitute in here because these are specifically equilibrium concentrations. Now how do we get these equilibrium concentrations from the initial concentrations is with the help of ice tables. So we would use ice table to solve this problem. Remember, ice tables are used when we are given initial and we are looking for equilibrium concentrations. I stands for initial, E stands for equilibrium, and C stands for the change. So let's first write on this equation. The equation that we have is SO2 gaseous. We don't have to worry about writing gaseous. Gaseous is just given to us because we know K equilibrium is only going to use gaseous entities or aqueous entities. So this is SO2 plus NO2 at equilibrium with NO and SO3. Here we write down I, C, E. I stands for initial, C stands for change, and E stands for equilibrium. These are all concentrations. So this is initial concentration, change in concentration, and equilibrium concentration. Now we would see, are we given initial concentration of SO2? Yes, we have already found that out, and that is 0.17. So we would put that here. Are we given initial concentration for NO2? Yes, that is 0.11. Initial concentration of products, if you're not given any products at first, is always 0. Now the change in concentration comes from stoichiometric coefficients with a variable. Here all of these stoichiometric coefficients are 1, so we would write down 1x. Remember, for reactants we have to put in minus because this is going to reduce. Here also it's minus 1x. Here it's plus 1x. Here it's plus 1x. Products are plus because they are going to be formed and they're going to increase their concentration. So their change is positive and the reactant change is negative. These numbers are decided by these stoichiometric coefficients. Variable is always we are going to use x. Now the equilibrium concentration is always the sum total of initial concentration and change concentration. So initial concentration is 0.17. When we add that to negative 1x, we get minus 1x. Similarly, equilibrium concentration here is 0.11 minus 1x. Here equilibrium concentration is 0 plus 1x is 1x by itself. Here also it's 0 plus 1x is 1x by itself. Now we have got the equilibrium concentration of, concentrations for each of the reactants and products, but we notice here that this is in the form of a variable. If we know the value of x, then we will be able to find out all of these equilibrium concentrations. So let's go back to the question and see if we are given something else that can help us find out this x value. We notice here that at equilibrium, the concentration of sulfur trioxide is given to us as 0.089 moles per liter. So that means at equilibrium, sulfur trioxide is 0.089 moles per liter. We also know that sulfur trioxide is 1x. Therefore, we can say 1x is equal to 0.089 because this is also equilibrium concentration and this is also equilibrium concentration. As both of these are equilibrium concentration for SO3, we can equate them and we can solve the value of x. So x is 0.089 divided by 1, which is 0.089 by itself. Now once we know the value of x, we can use this x value and substitute it everywhere and get all of these equilibrium concentrations. So we get 0.17 minus 1 times 0.089, which is equal to 0.081 0.1. When we put this value here, 0.11 minus 0.089, we get 0.021, and here 1 times x is 0.089 by itself. Now, since we know all of these equilibrium concentrations, we can again write down K equilibrium equation, and that is equal to SO3 concentration multiplied by NO concentration divided by SO2 concentration multiplied by NO2 concentration. All of these are at equilibrium. Now we have equilibrium values, so we will just put in the values here. So this is 1x, which is this, 0.089 times this is also 0.089 divided by 0.081 times 0.021. Just have to put this all in the calculator and we would get the answer 0.007921 divided by 0.001701, which is equal to 4.66, and that's the value of K equilibrium. And this is how we solve for K equilibrium when we are given initial concentrations or initial number of moles. We always first make the ice table, use the ice table to find out the equilibrium concentrations, and then plug in the equilibrium concentrations that we get using K equilibrium formula. Let's take up another example and let's read the question first. When solid carbon reacts with 2.25 moles of water vapor, solid carbon is C solid, reacts with 2.25 moles of water vapor, that means water in gaseous state. In 1 liter container, hydrogen gas is H2 and carbon monoxide forms. And equilibrium is established. Because equilibrium is established, we can write on K equilibrium. So K equilibrium will be equal to H2 raised to the power of 1 concentration multiplied by concentration of carbon monoxide raised to the power of 1 divided by the concentration of water raised to the power of 1. We're not supposed to include carbon in K equilibrium equation because this is a solid entity, and K equilibrium is only good for gaseous and aqueous entities that we learned in lesson number 1. Now we are given K equilibrium value. They want us to find out the concentration of each reactant and product in the gas phase. That means the concentration of H2O, H2 and carbon monoxide at equilibrium. So we have to find out their equilibrium concentrations. What we are given here is the initial value of moles of water vapor. We can use those initial values of moles of water vapor to calculate the initial concentration of water vapor, and that is 2.25 divided by 1. Number of moles divided by volume, and the initial concentration that we get for water vapor is 2.25 moles per liter. K equilibrium is 23.4. Now whenever we are given initial concentration, we know we have to use ice table that we learned in the previous question. How is this question different from the previous two questions is that in the previous two questions we found out K equilibrium. Here K equilibrium is given to us. We need to find out the concentration of the reactants and products. So we rewrite this equation. Carbon solid reacts with water gaseous and giving us hydrogen gaseous and carbon dioxide gaseous. We have to make ice table. Initial concentration of water is 2.25. Initial concentration of hydrogen and carbon monoxide is 0. Change is minus 1x because the stoichiometry is 1. Here it's plus x plus 1x. Equilibrium concentration of water is going to be 2.25 minus x. Hydrogen is 0 plus x is x. Carbon monoxide is 0 plus 1x is 1x. The K equilibrium value is now going to be 4x to the power of 1 times x to the power of 1 divided by 2.25 minus x. We know K equilibrium is 23.4. We would multiply this 23.4 value with this because we can bring this up there. So we would get 2.25 minus x equal to, we can multiply these two. X times x is x squared. Now our goal is to find out the value of x. Once we know the value of x, we can plug in the value of x in here and we can use that to find out our equilibrium concentrations of each of these gaseous entities. So we know this here, we can use FOIL method, this times this and this times this. 23.4 multiplied by 2.25 is 52.65. When we multiply 23.4 with x, we get 23.4x equal to x squared. Now since we are solving for x value and we see that this is a quadratic equation, we move everything on one side and this is what we get equal to 0. Once we get a quadratic equation and we need to solve for x, we use quadratic formula. So it's negative b plus minus root b square minus 4ac over 2a. That gives us negative 23.4 plus minus root b is 23.4 square minus 4. A value is 1. C value is negative 52.65 divided by 2 times a is 1, and we get is negative 23.4 plus minus square root of 758 divided by 2. That gives us negative 23.4 plus 27.5 divided by 2, as well as negative 23.4 minus 27.5 divided by 2. As we are looking for the change in the concentration of x, and we know concentration cannot be negative, this is going to yield a negative answer, so we'll cross this answer out. We would only use this, and we get 4.134 divided by 2. That gives us 2.07. So this is the value of x. This is not yet the concentration. We know x value we got is 2.07. So 2.25 minus 2.07 is equal to 0.18. Here x is by itself 2.07. Here also x is by itself 2.07. Therefore, the equilibrium concentration of hydrogen is 2.07 moles per liter. Similarly, equilibrium concentration for carbon monoxide is 2.07 moles per liter again, whereas the equilibrium concentration of water is 0.18 moles per liter. So this is how we get equilibrium concentrations using K equilibrium value. Let's do the last question. At 1400 degrees Celsius, hydrogen sulfide gas decomposes to give hydrogen and sulfur gas as follows, with K equilibrium value given to us as 2.4 times 10 to the power negative 4. If 4 moles of hydrogen sulfide is placed in 3-liter container, what is the equilibrium concentration of hydrogen gas at this temperature? Again, we're given initial moles of hydrogen sulfide in the volume of container, so we would get initial concentration of hydrogen sulfide first, and that would be equal to 4 divided by 3, which is equal to 1.33 moles per liter. Since we are given initial concentration, we know we have to use ice table here. We're also given K equilibrium value, 2.4 times 10 to the power negative 4. One more thing we have to learn here is called the hundreds rule. What is hundreds rule is, if we divide the initial concentration of the reactant, which is 1.33, with the K equilibrium value, which is 2.4 times 10 to the power negative 4, and the answer that we get is greater than 100, which we know it is going to be when we divide this on the calculator, then we say that the hundreds rule is applicable to the question. Now, where are we going to use this hundreds rule is after we write on the ice table. So let's write on the equation first. We have 2H2S giving us 2H2 plus S2. Initial concentration of H2S is 1.33. We are not given initial concentrations of hydrogen and sulfur, so that is 0. Change is minus 2x. Here changes plus 2x, here changes plus 1x. Equilibrium concentration is 1.33 minus 2x. This is 2x, this is 0 plus 1x is 1x. Now when we write on K equilibrium equation, we get the product of hydrogen concentration square and sulfur concentration divided by the concentration of H2S square. Now we plug in the values of K equilibrium. So hydrogen concentration at equilibrium is given to us as 2x. We would put 2x square multiplied by sulfur is 1x divided by 1.33 minus 2x square, and the value of K equilibrium is 2.4 times 10 to the power negative 4. We can write that here, 2.4 times 10 to the power negative 4. Now here is where we are going to be using the hundreds rule. Because the hundreds rule is applicable on this question, we can consider x to be very small and can be assumed to be 0 on the denominator. That means on the denominator we would be left with 1.33 minus 2 times 0 is 0 square. This hundreds rule make our life easier when K equilibrium is very small. So once this is 0, we do not have to solve for this 2x anymore. We just have 2 times 2 is 4x square times 1x over 1.33 square, and we have 2.4 times 10 to the power negative 4 here. When we multiply 4x squared with 1x, we get 4x cubed. This thing gets multiplied here, so we get 2.4 times 10 to the power negative 4 multiplied by 1.33 square. All we have to do is just isolate for x. When we put this all on the calculator, we get 4.25 times 10 to the power negative 4 equal to 4x cubed. We can divide this whole thing by 4, which is equal to 1.06 times 10 to the power negative 4 equal to x cubed. Now we know x is equal to cube root of, when we take this cube on the other side, so it's cube root of 1.06 times 10 to the power negative 4. And we finally get 0.05 as the x value. Now we were not looking for x value, we were looking for equilibrium concentrations. So we would use the 0.05 to get the equilibrium concentrations. We know 1.33 minus 2 times 0.05 is going to be equal to 1.23. Here 2 times 0.05 is equal to 0.1, and this is 0.05 by itself. Therefore, the equilibrium concentration of S2 is 0.05 moles per liter. Equilibrium concentration of hydrogen is 0.1 moles per liter. Equilibrium concentration of hydrogen sulfide is 1.23 moles per liter. And this is how we get the equilibrium concentrations once we know the K equilibrium, which is similar to the previous question. The only difference is that here we applied the hundredths rule, and hundredths rule is only applicable if the initial concentration of the reactant divided by the K equilibrium value is greater than 100. This is just to make our life easier when we are calculating the value of